Problem 8.7. Is a completely inelastic collision. We repeat the collision described in 8.5, but this time with the gliders, but this time they stick together when they collide. Find the common final x velocity and compare the initial and final kinetic energies of the system. So here we are before. We have glider A. This way, glider B. Going this way, A and B. A has a mass of 0.05 kg. B has a mass of 0.3, mass equals 0.50 kg. And B has a mass of 0.30 kg. And B has got a velocity of -2 meters per second. And A has got a velocity of 2 meters per second. All right, and so it's an inelastic collision, so when they collide, they stick together. So once again, we've got the momentum before equals momentum after. So we've got 0.5 kg times 2 meters per second plus 0.3 kg times a -2 meters per second equals, and once again, they're one system, 0.5 kg plus 0.3 kg times their combined velocity, which I'm going to take from the book, is going to be 0.5 meters per second. All right. Now I'm going to do their kinetic energies. So K A before equals, let's see, we've got A's got 0.5 kilograms, 1/2, 0.5 kgs times 2 meters per second quantity squared, 2.0 meters per second quantity squared equals, that's going to be 1.0 joule. And kinetic energy of B before equals 1/2, 0.5 kg times a -2, oh, this is 0.3, sorry. -2.0 meter per second. And that's going to equal to 0.6, oh, this is squared, 0 joules. And remember, this is a scalar. So kinetic energy is a scalar. So it doesn't have a direction, but anyway, this is squared anyway, but just wanted to throw that in there. Now the kinetic energy of the system after collision is going to be equal to 1/2 0.50 kilograms plus 0.30 kilograms times it was 0.5 meters per second quantity squared And that equals to 0.10 joules. 8.8 is the ballistic pendulum problem. We did a lab like this, but I'll do it again. You can't do a physics problem too many times. So you've got a, they're doing a bullet in a wood. They're shooting a bullet into a piece of wood that's pinned to some pin, and it raises against gravity. And they've got that H, delta H. All right, so you have two things going on here. You've got conservation momentum and conservation of energy. The conservation momentum, it's a perfectly inelastic collision, so momentum of the bullet, mass of the bullet times velocity of the bullet, plus mass of the wood times velocity of the wood is going to equal, once again, after collision, they get stuck together. Mass of the bullet plus mass of the wood times V final, if you will. All right, this guy is 0 since it is at rest, and this is the quantity we want. So we've got velocity of the bullet equals mass of the bullet plus mass of the wood times V final over mass of the bullet. And we still have two unknowns in our equation, so we can't solve, but we'll use conservation of energy to determine this quantity. So we know that that's going to be raised a certain height, so we're going to use our kinetic, we're going to do our 1/2 K amp, just do kinetic energy before equals potential energy after. Final. So we've got 1/2 M plus mass of the bullet plus mass of the wood times B final squared equals mass of the bullet plus mass of the wood times G times H. So I'm going to cross these guys out. I'm going to V final equals the square root of 2GH, and go ahead and substitute that value. So velocity of the bullet is going to be equal to mass of the bullet plus mass of the wood times the square root of 2GH over mass of the bullet. Do we have value? Yes. Wait, do we have values or just? We do have values, so I'll go ahead and solve that in 1 minute. Dry erase. All right, so what do we have here? We've got, they give us some numbers. Mass of the bullet is 5 grams. Mass of the wood is 2 kilograms. Height is that delta H is 3 centimeters. All right, so we've got velocity of the bullet equals 2 grams is, or 5 grams is, or 0.00005 kg plus 2 kg divided by 0.00500. Oh, this is 200 kg, 2.00. Times the square root of 2GH. So 2 times 9.80 meters per second squared. That's squared. Times 0.0300 meters. 0.0300 meters. And that's going to give us 307 meters per second. Wait, yeah. 307 meters per second. And they also did velocity 2 here. Velocity final is the square root of 2gh. 2 times 9.80 meters per second squared times h, which was 0.300 meters. And that answer was 0.767. All right. A9 is an automobile collision. And says a 100-kilogram car traveling north at 15 meters per second. So car equals 1,000 kilograms, sorry, 1,000, that'd be a small car, kilograms, and it's going this way at 15 meters per second. Collides with a 2,000-kilogram truck. Traveling east at 10 meters per second. So that guy's going this way at 10 meters per second. And the occupants wearing seatbelts are uninjured, but the two vehicles move away from the impact point as one. The insurance adjuster asks you to find the velocity of the wreckage just after impact. Okay, so we have, let's see, we're going to do the same thing that we did before, but by components. So we have, this guy is going to be 1,000. This is in the x direction. In the x direction. 1,000 kg times 0 plus 2,000 kg times 10 meters per second is going to be our momentum P in the x direction. All right, so our momentum in the x direction is going to be 2 times 10 to the 4th kilograms meters per second, this guy. 2 times 10 to the 4th kg meters per second. And this is P. P in the y is going to be equal to 10,000 kilograms times 15 meters per second plus 2,000 kg times 0. That's going to be equal to 1.5 times 10 to the 4. 1.5 times 10 to the 4th kilograms meters over seconds. Okay, we have the two components of the momentum. And now we will find the total component, the direction, and the velocity. So the total component, we know that P before equals P after, so P is going to equal to the square root of 2 times 10 to the 4th kilograms meters over second. This is squared. Plus 1.5 times 10 to the 4th again. Yep. kilograms meters over second. And that too is squared. And so this value is 2.5 times 10 to the fourth kilogram. So the after is going to be 2.5 times 10 to the fourth kg. The angle is going to be tan inverse of the y component over the x, so of 1.5 times 10 to the fourth kg meters over seconds divided by 2.0 times 10 to the fourth kg meters over second. And that angle is going to be 37 degrees. And let's see, and dividing by the mass, their combined mass here, V equals P over M. So that's going to be equal to 2.5, this over meters seconds, by the way, 10 to the fourth kilograms meters over seconds divided by 3,000 kg. And my velocity is going to be 8.3 meters per second. Okay, 8:10, an elastic straight line collision. Get this. All right. Okay, it says we repeat the air track collision of 8.5, but we add an ideal spring bumpers to the glider so that the collision is elastic. What are the final velocities of the collision? All right. So we are going to use the elastic collision and relative velocity equation along with the momentum. So we're going to say V B final minus VA final equals a negative VB initial minus VA initial. And then we know that is negative 2 meters and 2 meters. So we're going to have that's going to be equal to a negative 2 meters per second meters per second. That's not 20, that's 2. I don't know why this pen does not want to work on. That's a 2.0 meters per second minus 2.0 meters per second. And that's going to give us 4.0 meters per second. And then we go down to the momentum equation. And we have, let's see, we have a 0.50 kgs, 50 kgs. Momentum before equals momentum after times 2 meters per second plus 0.3 kg times a negative 2 meters per second equals, and we're just going to write it in terms of the final velocity. So we're going to have 0.5 kg times V A final plus 0.3 kg times V B final. And this is going to be equal to 0.4 0.40 meters per second. And now we take these two equations and we'll combine them and solve. Okay, so I had 0.5 VA final plus 0.3 VB final equals 0.40 meters per second. That's from the conservation momentum. And from the relative velocity equation, I had VB final plus VA final equals 4.0 meters per second. And I'm going just to rearrange that. I'm going to say VB final equals, this was minus, sorry, that was a minus, equals 4.0 meters per second plus VA final. I'm going to take this guy here and put it up there. I'm going to have 0.5 VA final plus 0.3 times 4.0 meters per second plus VA. And that's going to be equal to 0.4 meters per second. 0.4 meters per second. Distributing out and arranging these so that I get like terms on both sides, I'm going to get 0.5 VA final plus 0.3 VA final equals a 0.4 meters per second minus 1.2 meters per second. And when I, oh, this is 0.3. It's hard to read that, yeah. And when I do the math, I'm going to get VA equals -1 meter per second. Take that value and go back to, you could go back to this guy, and then solve for VB, which is going to be 3 meters per second. That was 810. This is problem, example 811. And it says moderating fission neutrons in a nuclear reactor. The fission of uranium nuclei in a nuclear reactor produces high-speed neutrons. Before such neutrons can efficiently cause additional fissions, they must be slowed down by collisions with nuclei in the moderator of the reactor. The first nuclear reactor, built in 1942 at the University of Chicago, used carbon as the moderator. Suppose a neutron, we'll have this N, mass equals one atomic unit, so we'll just do 1.0 U, traveling at 2.6 times 10 to the 7 meters per second. So V equals 2.6 times 10 to the 7th meters per second. Undergoes a head-on collision with the carbon nucleus. So carbon equals mass is 12 U, and it is initially at rest, so V equals 0. All right, neglecting external forces during the collision, find the velocities after collision. Okay, so we'll do that. So I'm going to use equation 825, which says this is for elastic collisions, one body initially at rest. So the velocity final of B, here's the equation, equals 2ma 2 mass of A divided by mass of A plus mass of B. And then that's going to be times the velocity initial of A, VI of A. So we've got velocity of carbon final equals 2 times 1U, that's the mass of the neutron, divided by 1U plus 12U, and that's times the original velocity of A, which is 2.6 times 10 to the 7th meters per second. And we'll get the velocity of carbon final equals, let's see, 2 over 13 times 2.6 times 10 to the 7th meters per second. And I get velocity of carbon final is, let's see, let me do this. Just had this on my calculator. On 0.4 times 10 to the 7 meters per second. 0.4 times 10 to the 7th meters per second. All right. Now I'll use the equation, that was equation 825, equation 824 to solve for the velocity of the final velocity of the neutron. And that equation is the velocity of B final equals, I'm sorry, that's the wrong one. Let me erase that real quick. All right, this is going to be the velocity of A final, VA final, which is the neutron, equals mass of A minus mass of B divided by mass of A plus mass of B, MA plus MB, times mass of A initial times velocity A initial. So we are going to have VA final equals mass of A is 1U minus 12 U's, and then divided by 13U times this 2.6 times 10 to the 7 meters per second. And your answer is going to be, I'll just take it from the book, it's going to be negative 2.2 times 10 to the 7 meters per second. Negative 2.2 times 10 to the 7th meters per second. The VA final, or V neutron final. And that's a 2. And then V carbon final is this guy. A12 is a two-dimensional elastic collision. Oh. All right. So weird whiteboard. It's not very responsive. Anyway, we have figure 8.27 shows an elastic collision of two pucks. Masses MA equals 0.500 kg. MA equals 0.500 kg. And MB equals 0.300 kg. MB equals 0.300 kg. Let's see. On a frictionless air hockey table, puck A has an initial velocity of 4.00 meters per second. the I equals 4.00 meters per second. And in the positive x direction, and a final velocity of 2 meters per second in an unknown direction. So VF equals 2.00 meters per second, direction unknown. Find the final speed v and the angles alpha and beta. So here's the diagram. We have this guy colliding with this guy at rest. This is A and that's B. And after collision, we have something like A going that way and B going this way. All right, so now we need to find. So the collision is elastic, so we know the initial, final, and kinetic energies of the system are equal. So we have 1/2 MA, the kinetic energy of A, plus B, which is 0 in before collision. So this is 0.500 kg times 4.00 meters per second, quantity squared, equals 1/2 times 0.500 kg times 2.00 meters per second, quantity squared, plus 1/2 times 0.300 kg times V final squared. And if you do the math, V final of B is going to be 4.47 meters per second. So I'll do that. The initial of B was 0. V final is 4.47 meters per second. Let me pause and clear the board. All right, now we are need to find the angles, and so they have the scenario here of A going off here, and they call this guy alpha, and B going here, and this guy is beta. All right, so we're going to do the conservation of momentum in the X and Y directions. All right, so let's see, we have, for the X direction, we have a 0.500 kg times 4 meters per second. That's in the X direction. P sub X equals 0.500 kg times 2 meters per second cos alpha. Cos alpha plus 0.300 kg times 4.47 meters per second. And then that would be cos beta. All right, that's in the X direction. For the Y direction, I have no initial momentum, so I have 0 equals 0.500 kg times 2 meters per second sine alpha. And then this guy's going in the negative Y direction, so minus 0.300 kg times 2, no, that's 4.47 meters per second times sine beta. All right, clearing up some space. Okay, so I was here, 2 kg meters over second equals 1 kg meters over second times cos alpha plus 1.3, that's a 3.34 cos beta. And then I had a 1, well, this has got to have the units, 1 kg meters. Ugh, this whiteboard is horrible. 1 kg meters over second sine alpha equals 1.34 kg meters over second sine beta. Okay, I'm going to take away all these signs and everything, and I'm going to do this. I'm going to write this once I distribute and take away the units. It's going to be 1.34 cos beta equals 2 minus cos alpha. And I have 1.34 sine beta equals sine alpha. All right, now I'm going to square both equations and I will get 1.84 cos squared beta equals 4 minus 4 cos squared alpha plus cos squared alpha. And on this side, I get 1.84 sine squared beta equals sine squared alpha. All right, adding these guys, both sides of the equation up, I'm going to get 1.84. Because when I add cos squared and sine squared, it gives me 1. Equals, and that's going to be equal to 4 minus 4 cos squared alpha, and then plus 1, because this sine squared alpha and cos squared alpha are equal to 1. And then you could just solve from there. So the key is to write these in terms of each other, square both sides, and add both sides of the equation. 8.13 is the center of mass of a water molecule. Figure 8.28 shows a simple model of a water molecule. The oxygen-hydrogen separation is D equals 9.57 to the negative 11th meters. So D equals 9.57 times 10 to the negative 11 meters. And that is, I guess, yeah, we got something like this. And D is R, the distance from the center of mass of the oxygen to the center of mass of each hydrogen. And let's see, each hydrogen has a mass of 1 U, the oxygen has a mass of 6 U. Find the position of the center of mass. We know that these are separated by an angle of 105, so each angle is going to be 52.5. This is all right. Okay, so we're going to do the X center of mass and the Y center of mass. So we've got X cm equals the sum of the masses times the radius over the sum of the masses. So we've got equals 1 U, just 1. We'll just call that 1 times D cos 5.25. So this is this X center of mass. D times cos 5.25 plus 1U times D cos 5.25, right? These guys are both in the positive. 1 times D times cos 52.5, not 5.25. Cos 52.5. And then that's all over 1 plus 1 plus, what was the other one, guy? 16U. And then that's going to be equal to 0.068 D. So X center of mass, 0.068 D. So this times 0.0 times that. All right, and then for the Y center of mass, it's just going to be Y because these guys are symmetric. But we can do that. Let's go ahead and erase some of this. So what I'm going to have is 1 times D times sine of 52.5. And then that's going to be minus 1 times D times sine of 52.5. So that's just going to give you, and that's going to be over 1 plus 1 plus, what was that? 16 plus 16. And that's going to give you 0. So you've got an X center of mass of 0.068 D. So that's going to be 0.068 times 9.57 times 10 to the negative 11th meters. And we're going to get a 6.5 times 10 to the negative 12 meters. 6.5 times 10 to the negative 12 meters. Very good. All right, 8.14 is a tug of war on ice. James mass 90 kg. James mass equals 90 kg. 90.0. And Raymond's mass equals 60 kg. They are on frozen pond, and midway between them is their favorite beverage. They pull me under the light rope strips to feed them. When James has moved 6 meters towards the mug, how far and in what direction? So we got these guys here. We got Raymond, James, and here's the midway point, and here's their mug of their favorite beverage. Okay, and that's 0. So now I need to find the center of mass. All right, so the XCM, it's only in the X direction, equals the sum of the masses and the distance from the center times the total masses. 90 kg. How long is that rope? That rope is 20 meters apart. So this is total 20 meters. 20 meters. So each of them are 10 meters from the mug. So that's 90 times negative 10 meters plus 60 times a positive 10 kg, sorry, times 10 meters divided by 150, right? 150 kg. And the X center of mass is going to be equal to a -2 meters. So here's the center of mass. That's -2 meters. All right, so the center of mass isn't going to change, so we've got to figure out, they're pulling each other forward and they're going to slide, and we assume the rope isn't going to stay taut. So we have a -2 cm equals 90 kg. And let's see, he is 6 meters towards a mug. So that's going to be times a -4 meters plus 60 kg times a x. That's what we want to find out. How close is he to the center? Divided by 150 again. Equals, and that's going to be, x2 is going to be equal to 1.0 meters. 1.0 meters. So he's going to be 1 meter from here on this side. He's going to have moved 9 meters. 9 meters. All right. 8:15 is acceleration of a rocket. The engine of a rocket in outer space far from any planet is turned on. The rocket ejects fuel at a constant rate. In the first second of firing, it ejects 1/20 of its initial mass, MO, at a relative speed of 2,400 meters per second. What is the rocket's acceleration? We're going to use the equation A equals dx over m times dm dt. And now we'll solve for dm dt. dm dt equals, it's going to be 1/120 of m original over how much was d? 1 second. 1 second. So it's going to be mo divided by 120 second. All right, and now A equals V of the exhaust over MO times dm dt, and that's going to equal 2,400 meters per second divided by MO times, oh, this is a negative MO, right? It's getting smaller. Negative MO over 120 seconds. And that's going to equal to 20 meters per second squared. All right, 8:16 is the speed of a rocket. It says suppose that 3/4 of the initial mass of the rocket, in example 8.5, is fuel. Final mass of the rocket is m equals mo divided by 4. M equals mass original divided by 4. And let's see, if the rocket starts from less than our coordinates, we find its speed at the end of the time. And to do this, we're going to use the equation 8.4, which says V minus V naught equals negative Vx exhaust times ln of m over m. So we know that V naught is 0. This is 0, right? Starts from rest. So V equals negative. Wait a minute. Oh, we just switched the m and m. Okay, so we're going to have a equals positive Vx ln mo over m. So V equals Ex ln mo over m. So V equals 2,400 400 meters per second. ln of MO over 4 over MO over MO over 4. So that's going to be equal to 2,400 meters per second times ln of 4. And that's going to be 3,327 meters per second. 3,327 meters per second.